With this other question, what do we have here now? I'm not going to read the question. I'm read the question which just says, solve the differential equation. Anyway, here's the differential equation. Let's get to solve it. So differential equations are just a stretch. They're just another form of integration, only that they have one other step. So let's copy it down and let's see. 1 over 5x plus 1 multiplying sine squared 2 theta. All right, so now let's get to work, right? So differential equations, you see, differential equations have two types. One where you actually have to develop a differential equation and then solve it. And then one where you're already given and you just have to solve. So how do you solve differential equations? It's by integration. But before you integrate, there's just one thing you always do before you start integrating, okay? That's for the differential equations you meet. And that is what we call separation of variables, all right? At your age, you should know how to do something called separation of variables. So what is that? You are going to take things that are like to one side, okay, and then you remain with the things that are like on the other side as well. So it's like you just separate the things to make sure that dx will meet things that have x, and then d theta will go to things that have theta. So since d theta is in the denominator, we'll obviously take him to the right, which means dx remains on the left. That means everything with x has to come to the left where dx will be. So this thing with left is coming to the left. It was multiplying. When it comes to the left, it should divide. So we put it as 1 over 5x plus 1, right? And the dx would have remained. This is now equal to sine squared 2 theta was there on the right, and d theta has come there now. Now, once we get to this stage, we have done the first step, which you always do, which is called separation of variables. Now, when you do this, what do you then do? You start integrating. So let's zoom in so that we can be able to do it. I don't want to waste space because we're going to need all the space we can find. So let me move this up here. All right, so now let's start. Okay, so what are we going to do now? We're going to introduce integration. So integral of 1 over 5x plus 1 with respect to x is equal to integral of sine squared 2 theta d theta. Now let's quickly do these integrations. These are easy integrations. Let's quickly go through them. So what is the integration technique that I'm going to use on the right? I'm going to see that it's a fraction on the left, Or should I start with the right? Okay, let's start with the right. What do I have? I have sine squared 2 theta. What is the integration technique that I use on sine squared 2 theta? So you do not integrate sine squared, and you cannot integrate cos squared. When you see them, you always go to MF19 and you go to where it says cos 2a, the double angle for cos. That is where you go for both of them. If you see a sine squared and a cos squared, don't try to integrate them. It's impossible. Go to MF19, go to the double angle for sine of for cos, for cos 2a. And that is where all the formulas are going to be. Let's go then. Here's the MF19. I've opened it. Here's our MF19. Now, what are we going to do? We're going to scroll down, right? Let me scroll down. I'm going to scroll down until I get to trig page, which is here, and I go to for cos 2a, which is here. This is where that is the same one I use to integrate a cos squared and a sine squared. Okay, when I have a cos squared and a sine squared, do not forget, I don't care what it's cos squared of 2 theta or theta or whatever, but when I have a cos squared and a sine squared, I have to come here, and I'm going to, let's see here. How do I know what to do when I have a cos squared? I pick this one. Cos 2a is equal to 2 cos squared a minus 1, right? I ignore this first one, okay? So I can say cos 2a is equal to 2 cos squared a minus 1, right? Then what am I going to do? I'm going to make cos squared the subject. It tells me. I take 1 to the other side. It's going to be 1 plus cos 2a is equal to 2 cos squared a. Then I take the 2 to the other side, it will divide and it will be just a half. So it's half of 1 plus cos 2a. This is equal to cos squared a. So now I know what my cos squared a is. What is cos squared a? It's half of 1 plus cos 2a. This will give me cos squared a. Are we saying this? I hope you're saying this. So I now have, whenever I have a cos squared, I'm going to change it into this. Okay, but there's something I need you to realize that is going on here. And it is that you'll be having a cos squared a. When you change it, it will be half 1 plus cos 2a. You double whatever angle you had on the cos squared. If it was a cos 3a, you double it to become a cos 6a. You always double that. Okay, now let's do for sine squared. We'd still use this cos 2a, but we take the last one, which is 1 minus 2 sine squared a. So now we can say here, we can say that cos 2a is equal to 1 minus 2 sine squared a. That's what it has. Now I make sine squared the subject, okay? How? I take it to the other side to make it positive. So I have cos 2a plus sine squared a is equal to 1. Then I take cos a to the other side. I'll have sine squared. Okay, it's not just a sine squared, but it's a 2 sine squared. So plus, this is 2 sine squared. So now I'll take cos 2a to the other side. I'll have 2 sine squared a is equal to 1 minus cos 2a. Then I take 2 to the other side. I'll have sine squared a be equal to half, then 1 minus cos 2a. So do you see for sine squared, it is what? Half 1 minus cos 2a. Remember, you should double the angle. Okay, this was a sine squared a. Can you see that? It was a sine squared of a here. Sine squared of a, it will become cos 2a. Double, you double it. That's what you should do. Now let's go back to see. So for cos 2a, for cos squared a, it is half 1 plus cos 2a. For sine squared, it is half 1 minus cos 2a. But the other one is 1 plus cos 2a. For cos squared, it's 1 plus cos 2a. It's a half of 1 plus cos 2a. For sine squared, it's half of 1 minus cos 2a. Let's go and do finish. So now let's do for sine squared. We saw that this is going to be the integral of half. Then we say 1 minus cos. Then you double whatever angle. So here it's sine squared 2 theta, so it will be half 1 minus cos 4 theta. Don't forget to double it with respect to theta. Then once it's like this, it's going to be easy to do it. Now let's talk about the fraction. Fractions, yes. We want to integrate, yes. How do we integrate fractions? When we differentiate fractions, we use the chain rule, the quotient rule. How do we integrate fractions? We have 3 cases. You say, are you sure? Yes. One which is using u sub. Then the other one, which is the one which will give you a tan inverse of x. Then the last one, which is the one which will give you an ln x. Let's see the one which uses u sub. Let's talk about it. Let's talk about it. Let's talk about it. Let's talk about it. So if you get an integral and you have the denominator being a composite function. Composite functions are of many kinds. You know, I've told you, be careful. You know Lie-8, right? You know the 5 types of functions in Lie-8, right? Liate. Logarithmic, ln x, inverse trig, tan inverse of x. That's the one you're going to meet. Algebraic are just those x squared plus 5x minus 7, or the square root of x, okay, plus 2x minus 9. Things like this, okay. Then t is for the trig, the 6th trig, sine, cos, tan x, okay, sine x, cos x, tan x. Then sec x, then cot x, then cosec x. The 6th, then this is e to the x. So here we have these like, if you get anything which is not like these, then you'll be having a composite function. For example, if you get 1 over, let's talk about the composite function, x squared plus 5 all to the power of 7. What is this? This is a composite function any day of the week. Any day of the week, because the polynomial is just this thing inside, x squared plus 5. Why does it all have to be raised to the power of 7? Once you see you raise yourself the whole thing to the power of something, then you are having a composite function. Okay, or we say it, if you get ln of something which is not x, ln of x squared plus 5, this is a composite function. It's ln of something which is not x. Once you see these functions which I've given you and you see them have something which is not an x, anything which is not an x, for these ones here, for polynomials, you see them have a big root for covering everyone, or a power covering everyone that will be outside. That's a composite function. For e to the x, you see it being e to the something which is not an x. That's a composite function. Once you have such a situation, the only way to differentiate it is to use the chain rule. And the only way to integrate it is to use the reverse chain rule. But now, if you get it in a fraction, okay, and you are integrating, okay, you want to integrate in a fraction, well, now, and you get it like this, and the top is a version of the derivative. So if I differentiate an x squared, I get some type of x. So let's say on the top it's a 2x. You can see that the top is the derivative of the inside of the denominator. The denominator is composite. It is composite. And the top is the derivative of the inside of the denominator. Once you have an integration like this, you use u sub. U sub is when the top is the derivative of the inside of the denominator. The denominator will be composite. But if you differentiate the inside of that composite thing and you get the top, then you are supposed to use u sub if you are to integrate such a fraction. You understand? It's a fraction. That will be like that. Let's say you are integrating 3x squared over sine 3x with respect to x. What should I use here? Okay, I see that the denominator is composite. Yes, because it's sine of something which is not an x. Now, if I differentiate the inside, let's say it is x cubed rather. Sorry. Sine of x cubed. Let's say I differentiate the x cubed, the inside now, the inside of this sine. If I differentiate it, what do I get? I get a 3x squared or something like that. That makes this a u sub question, because if you differentiate this inside, you are getting the guy on the top. So what do we have here? We are having a u sub question. It's a fraction, and the inside of the denominator will be differentiated to give the top. So you use u sub, and you always let u be equal to the inside, okay? That inside thing. Are you seeing how it's going so far? Are you seeing the ones for u sub? The top will be a version, even if this was an x squared, okay? We still can use it because x squared is a type of derivative for x cubed. Remember, when you differentiate an x cubed, the power goes down by 1. So the top must just have 1 power less or whatever, the derivative of the inside of the denominator. Then we are going to use u sub. That is a clear u sub integration. Do not forget that I've told you. You can't forget. You only have 3 possible methods when you're integrating a fraction. All right, you only have these 3 here. You understand? Okay, let's talk about the other one now. Okay? Now let's talk about the other one. I don't want to hear anyone say, what about the one for partial fractions, whatever. For partial fractions, they'll make you partialize before you even integrate. So don't worry about it. I won't even talk about it. We're not talking about it. The possible ones are u sub. And u sub, we said the top is the derivative of the inside of the denominator. You're supposed to integrate that. You use u sub. Okay? U sub is not for differentiation. There is no such a technique. In differentiation, it is product rule, chain rule, power rule, quotient rule. Those are the rules for differentiation. Differentiation of implicit functions, differentiation of parametric functions. But once we are now doing integration, we now start to talk about u sub. We start to talk about these by parts and whatever these other techniques. And with the techniques we're talking about, when we have a fraction, is one u sub, then the other one, the integral, which will give you tan inverse of x. Let's see what it would be. What type of integral do I do for me to get a tan inverse of x? Because I know that I can differentiate tan inverse of x and get something. The derivative is there. It is there in your MF19. And also the integral is there. But I just want you to make sure you know about it. Let's talk about it. If you integrate something which is going to be like this, let me show you. If you integrate something which is, for example, 1 over 1 plus x squared, and you're integrating this with respect to x, I want you to see 2 things here that are of notice. Number 1 is that the denominator will have an x squared. Can you see that? The denominator has an x squared, and the top is a 1. So it's 1 over 1 plus x squared. If you're integrating this, then you're just going to get your tan inverse of x plus constant of integration c. This is what you have. And if you integrate 1 over some number, but you put it as some number squared, plus x squared, and you're integrating with respect to get, then you're going to get 1 over a tan inverse of x over a plus c. Look at what you should see here. Is that it should be an x squared. It should be an x squared, class. It should be an x squared, or else it's not the one which gives you tan inverse. Okay, if you see an x squared and a 1 on the top, this number, you change it to something squared, okay? You square it, then square outside, so that you can now write this. And when you pick, you leave the squared, you just pick the number itself, and it's the one you're going to put over here. And that's the version you're going to get. So for tan inverse, we're going to get it. So now let's go and check the integral we have. Maybe it's one of these 2 methods we've just talked about. This integral is the integral of 1 over 1 over 5x plus 1. Number 1, let's try to check for u sub. Is the denominator a composite function? No, it's not. It's just an algebraic function. There's no power which is affecting that whole thing. So it's not a composite function. So u sub is out. U sub has to have a composite function. And the top will be the derivative of the inside of that. So u sub will throw you out. Now, let's see. Do we have an x squared for us to check one of these cases? I see there's a 1 on the top. Fine. But do we have an x squared? No. It's 1 over 5 of x. So tan inverse, you are out. So that means we are already left with only the integral which will give us ln, right? Remember, we have the integral which we use u sub, then we have the integral which will give us tan inverse. You have seen the integral which gives us tan inverse. Now there's an integral which gives us ln of x. And what is that integral? It is just when you integrate the top being a derivative of the bottom. Look at this. You say, isn't this u sub? No! We said u sub, the top is the derivative of the inside of the bottom. For ln, for the one which gives you ln, the top is the derivative of the bottom itself. Not the inside of the bottom, but the bottom itself. Okay? So if I differentiate the bottom and I get the top exactly, that means I'm going to just say this will give me ln of the bottom. Okay? ln of the bottom plus constant of integration c. So if I see here, sometimes you may have to do some adjustments. I'll show you when I'm doing the question. If I see here, if I differentiate in x, do I get a constant? Yes. So I can see that the 1 over 5x plus 1, if you differentiate this, you get a 1 over 5, which is just a constant, okay? Which is just similar to this one. So I can see that the top is the derivative of the bottom. So what do I use? This is the integral, which will give me ln x. Okay? So now I want to stop the video here, and we'll start in the next one where I apply. I hope you have seen how I've chosen the method. Now in the next video, we're going to apply it and finish it up, and we'll see the solutions. Goodbye for now. Let's meet in the next one.